this webinar. Today we want to take you through what's new in IBM SPSS Statistics version 32. My name is Astrid Cook, and I'm an analyst here at version 1. Now this webinar is looking at new features in IBM SPSS Statistics version 32, and the focus is really on new analytical procedures. So we'll look at mediation analysis, vector autoregressive models, Bayesian variable selection for regression, permutation tests, mixed type clustering, and then at the end, we'll cover off some more new features in the latest version. So now let's look at mediation analysis. In IBM SPSS Statistics version 32, there's now built-in mediation analysis. This is a statistical method that is used to understand the mechanism through which an independent variable influences a dependent variable through one or more mediating variables. So it helps you test hypotheses about indirect effects and understand the pathways of influence in your data. This is so you can analyze direct, indirect, and total effects without the reliance on extensions or custom syntax. You'll be able to find it when you go to the Analyze menu and you select Mediation Analysis. Now, there are some concepts that we need to review. So first of all, we have the predictor variable. This is our independent variable whose effect you want to examine. So an example would be treatment exposure or intervention level. We have the mediator variable. This is the intermediate variable that transmits the effect of the predictor to the outcome. So an example might be psychological state or biological marker. We have the outcome variable. This is the dependent variable that is affected by both the predictor and the mediator. So an example here could be health outcome or performance measure. We have the direct effect, which is the effect of the predictor on the outcome that does not operate through the mediator. We have the indirect effect. This is the effect of the predictor on the outcome that operates through the mediator. And we have the total effect, and this is the overall effect of the predictor on the outcome, combining both direct and indirect pathways. Now we have two analysis approaches. We can use causal mediation analysis. This computes comprehensive causal effects, including control direct effect, natural direct effect, natural indirect effect, and decomposition components. This approach allows for predictor-mediator interactions and provides detailed effect decomposition. You have traditional mediation analysis. This computes simpler mediation effects without interaction terms or detailed decomposition. This approach is appropriate when you do not expect interactions between the predictor and mediator. Now, it's important to point out that the procedure accommodates different combinations of variable types. So you can have a continuous predictor, continuous mediator, and continuous outcome. You can have a continuous predictor, binary mediator, and continuous outcome. You can have a continuous predictor, continuous mediator, binary outcome, continuous predictor, binary mediator, binary outcome, and continuous predictor, continuous mediator, and count outcome. Now, with statistical methods used, the procedure uses regression-based approaches to estimate mediation effects. We have linear regression for continuous variables, logistic regression for binary variables. We've got Poisson or negative binomial regression for count variables. Now, standard errors and confidence intervals can be computed using either the delta method, which is default, or bootstrap resampling. I'll show you where this sits within the dialog box, but you can see here we have the inference type area, and you can select delta or bootstrap. Now, in this demonstration, I'm going to use a simple example that tests whether BMI mediates the relationship between age and systolic blood pressure. Now, in the dialog box, I'll click on type of model. My mediator type is continuous. My outcome type is continuous. When I click on the dependent variables tab, I'll move my outcome variable here and my mediator variable under the mediator variable box. When I click on predictor, I'll move age into the primary predictor box. Now, we'll also need to click on set baseline level. So I'll set baseline level and new exposure level. Now, age was designated as a predictor variable. With a baseline level set at 35 years and an end level at 60 years, this represents a 25-year age span for effect estimation. Now, the analysis can also include an interaction term to test whether the relationship between age and blood pressure varies across BMI levels. When I click on the Criteria tab, I can choose between covariance matrix options, the inference type, delta versus bootstrap, The analysis type, here, causal and traditional. When you click on the Print tab, you can ask to print, for example, decomposition analysis results, interaction effect analysis, ratio statistics, descriptive statistics, covariance matrix, and case processing summary. For plots, you can choose from a path diagram, scatter plot, or forest plot. So here we have the mediation regression model summary table. And when we look at age, we can see that age has a statistically significant positive association with the mediator, which is BMI. But when we look at R-square and adjusted R-square, we see that the model explains a very small proportion of the variance in BMI. It's about 1.9%. Now, it's important to mention as well that the diagnostic checks show no issues with multicollinearity or autocorrelation, but the residuals do deviate from normality, and there are influential cases. So when we look at these results, we do want to interpret them with some caution. Now, here we have the outcome regression model summary, and we can examine age and BMI and the estimates. And what we see is that both of them are statistically significant predictors of the outcome. When we look at R-square and adjusted R-square, we now see that the model explains approximately 23% of the variation in the outcome, indicating moderate predictive power. When we look at diagnostic checks, these show no issues with multicollinearity or autocorrelation, but residuals do deviate from normality, and we do have influential observations. We can also look at the decomposition analysis and ratio statistics tables. Now, looking in the decomposition analysis table, we'll look at total effect, and we see that increasing age is associated with an overall increase in systolic blood pressure. If we look at the direct effect, we can see that the majority of this effect is direct, indicating that age influences blood pressure independently of BMI. If we look at the indirect effect, this is a smaller but statistically significant proportion of the effect that is mediated through BMI. Looking at the ratio statistics, we see that BMI mediates approximately 9.83% of the total effective age on systolic blood pressure, while about 90% of the effect is direct. So BMI does explain a small but statistically significant part of the relationship, but the majority of the effect of age on blood pressure occurs through other pathways. Now, in our output, we'll obtain visualizations, so we can examine the forest plot as well as the mediation path analysis diagram. So let's see how this works in IBM SPSS Statistics. Now, to get started with mediation analysis, go to the Analyze menu and come down to Mediation Analysis. I'll click on it, and this opens up the dialog box. So on the Types of Model tab, the mediator type is continuous, so this is BMI. Outcome type is continuous, so that's blood pressure. Dependent variables, blood pressure will move into the outcome variable area. BMI is my mediator variable. Now, the Set Mediator Level button, I can set the mediator level. Here I'm setting it at mean. I'll click on Predictor. My primary predictor is age. Now here I could add factors and covariates if I wanted to use those. For age, I'll set baseline level and exposure level. Criteria, I can select covariance matrix, inference type, analysis type. Analysis type, I'm choosing causal. For print, I want to print the decomposition analysis results, interaction effect, ratio statistics, and descriptive statistics. Now, also too, covariance matrix and case processing summary are turned on by default. For plots, I'd like path diagram. I'll ask for edge color type-based, and I'd like to see a forest plot. And when I'm ready, I'll click OK and run the analysis. In our output, we have the case processing summary. So we'll be able to see the number of cases that are clean versus the number of cases that are removed. Below that, we have the variable descriptives. And below that, we have the mediation regression model summary. Now, we'll look at age, and we see that age has a statistically significant positive association with BMI. But The model explains a very small proportion of the variance. We can see that with R square and adjusted R square. The relationship between age and BMI is statistically significant, but weak in practical terms. If we look at the outcome regression model summary, we can look at age and BMI. Both of these are statistically significant in the outcome model, supporting their roles in the mediation pathway. We can see that R square and adjusted R square have increased. Here we have the decomposition analysis table. We can look at total effect, and we see that increasing age is associated with an overall increase in systolic blood pressure. If we look at direct effect, we see that the majority of this effect, approximately 90%, is direct, and this indicates that age influences blood pressure independently of BMI. We could look at the indirect effect, and we see that we have a smaller but statistically significant proportion, about 10%, of the effect that is mediated through BMI. We can also evaluate the ratio statistics. So these are proportions of the total effect and can be interpreted as percentages. So we'll see that BMI mediates about 10% of the total effect of age on systolic blood pressure, while about 90% of the effect is direct. We can evaluate the mediation analysis forest plot, and we can evaluate the path diagram. And this diagram visualizes the mediation model. So now let's talk about vector autoregressive models. A vector autoregressive model is a fundamental tool in multivariate time series analysis. The concept is to extend the idea of autoregressive models, which explain a variable in terms of its own past values, into the multivariate case, where multiple interrelated time series are modeled together. The model captures the linear interdependencies among multiple time series variables. So the model expresses each variable as a linear function of its own past values and the past values of all other variables. So when would you use a vector autoregressive model? Well, you use it when you have multiple time series that influence each other over time, and it's not just one variable influencing another. Variables are interdependent, relationships are dynamic, lagged over time, and the direction of influence is not one way or obvious. Now, in the example that we'll look at, a retail company wants to develop a forecasting model, and they have data on monthly sales of men's clothing. They also have related time series that can help explain variation in the sales performance of men's clothing. So the objective is to understand how sales in other product categories can influence men's clothing sales. Now, the steps in the analysis will include defining date and time, stationary check, model estimation, lag order selection, model diagnostics, and forecasting. Now, in the data set, I've already defined date and time and performed the stationary check. It's important to remember that a stationary time series is one whose statistical properties, such as mean, variance, and autocorrelation, remain constant over time. Now, to access the procedure, go to the Analyze menu, select Forecasting, select Multivariate Time Series, and click on Vector Autoregressive Models. This will bring up the dialog box. There are tabs across the top, so when you click on the Variables tab, you can select your variables. Now, I've moved men's clothing sales, women's clothing sales, accessory sales, and shoe sales into the endogenous variables area. You have the lag selection area, so you can select your lag. Statistics, select the statistics you'd like to evaluate in your output. We also have the Plots tab and the Save tab. So you can select the plots that you would like to evaluate in your output. Save, you can save predicted values and noise residuals. Finally, we have the Options tab. Here you can determine forecast periods. So you might choose first case after the end of estimation period through last case in active data set, or first case after the end of estimation period through a specified date, and you would specify the date here. Now here we can focus on sales of men's clothing. The model suggests that men's clothing sales are influenced more by related category behavior, such as shoes, than by their own past performance. And this highlights the value of multivariate modeling over simple time series. Shoe sales from the previous period have a statistically significant positive impact on men's clothing sales. We see that here. Women's clothing sales from 2 periods ago show a statistically significant negative relationship with men's clothing sales. And we see that here. Now we can also look at goodness of fit. Now, the model selection criteria indicate that a lag of 1 provides the best balance between model fit and complexity. While a lag 2 model identifies some additional cross-category relationships, these do not sufficiently improve overall model performance. So this suggests that the most useful predictive information is captured within a shorter time horizon. We can also assess model fit statistics. We can look at R-square and adjusted R-square. The results suggest that while there are some relationships between categories over time, much of the variation in sales remains unexplained, and this highlights limits in predictability using just lagged variables alone. We could consider adding exogenous variables into the model, such as marketing actions. We can also examine tests for residuals. Now, these tests show no significant autocorrelation in residuals, and this confirms that the model adequately captures time-based patterns. Residuals are approximately normally distributed across most variables, with a minor deviation for shoes. Now here we can look at the fit values plot for men's clothing. You can observe fitted and the observed, and we see that fitted values track the underlying trend, but fail to capture sharper movements in the data. And this suggests that important drivers of sales variation are not being fully captured by the model. So here we might consider adding exogenous variables into the model. So let's see how this works in IBM SPSS Statistics. So I'm in IBM SPSS Statistics, and to get started, I'll go to the Analyze menu, come down to Forecasting, and then select Multivariate Time Series and Vector Autoregressive Models. Now, this brings up the dialog box, and I'll click on the Variables tab and select the sales categories that I want to move into the endogenous variables area. I'll also select my maximum lag. When I click on Statistics, I can select the statistics that I'd like to include in my output. Plots, I can select plots. Save, I can save predicted values and noise residuals. And the Options tab allows me to control forecast period. Now at this point, all I want to do is evaluate the model. So I'm going to click OK and run this so I can obtain my results. So now we can evaluate our output. At the top, we have the table of descriptive statistics. Beneath that, we have the model parameters table. So here we're looking at men's clothing sales. Now we are interested in this category. We have our coefficients, standard error, t-value, and significance. When we looked at the model, we found that men's clothing sales are influenced more by related categories or related category behavior than by their own past performance. Shoe sales from the previous time period have a statistically significant positive impact on men's clothing sales. So we see that here. Women's clothing sales from 2 periods ago show a statistically significant negative relationship with men's clothing sales. And we see that here. We can also look at women's clothing sales, accessory sales, and shoe sales. We can evaluate the goodness of fit. Now, this demonstrated that the lag of 1 provides the best balance between model fit and complexity. We can evaluate model fit statistics. So there are some relationships between categories over time. Much of the variation in sales remains unexplained. And at this point, we might consider whether or not we want to add exogenous variables. We can examine tests for residuals. And if we come down and we look at the fit values for men's clothing, we can look at fitted from the model versus observed. We see that the fitted values do track the underlying trend, but they fail to capture sharper movements in the data. And this suggests that important drivers of sales variation are not being fully captured by the model. So let's see how this works in IBM SPSS Statistics. So now let's look at Bayesian variable selection for regression. Now this is an extension, so you will need to install it from the Extensions menu. So to install it, go to the Extensions menu and click on Extension Hub. And then once you're in the Extension Hub, you can search for Bayesian Select Regression Variables. Once you've installed it, you can find it when you go to the Analyze menu and select Generalized Linear Models. Now, the extension provides a Bayesian method for selecting independent variables for linear and generalized linear regression models. Bayesian variable selection for regression is a regression approach that uses Bayesian statistics to automatically select the most important predictors in a model. So instead of deciding manually which variables to include, the procedure treats model selection as a probabilistic problem. It will evaluate many possible models, and it assigns each variable a probability of being relevant. And it produces a distribution of plausible models, not just one best model. Now, once you have the dialog box open, you'll select your dependent variable and then choose your independent variables. Optionally, you can select forced variables. Make sure you choose the error family and link, and then display plots. In our output, we can view and compare the top models, and we can see the variables that are included. We can also see important predictors. So these are age, education, children, and whether or not they live in an urban area. We can also examine model statistics. And what we'll see is that Model 1 is strongly supported as the best model with the highest posterior probability and the highest log marginal likelihood. We can see that here. Model 1 and Model 2 have identical R-squared values, but Model 1 is preferred because it achieves the same explanatory power with fewer variables and a higher log marginal likelihood. And this highlights a key advantage of Bayesian model selection. It favors parsimonious models that balance model fit with simplicity. We can also examine the posterior coefficients table, and we'll see strong evidence for age, education, children, and urban. In contrast, income has a much lower probability, and this shows weak evidence and suggests that this variable does not meaningfully contribute to the model. We can examine the residuals versus fitted plot. When we look at this, we don't see an obvious pattern, and this suggests that the model is correctly capturing the linear relationship between predictors and the outcomes. We don't have evidence of homoscedasticity in that the spread of the residuals is fairly consistent across fitted values. You can see some outliers, and these cases may deserve investigation. We also have the model select heat map. Now, on the x-axis, you'll be able to see the variables. On the y-axis, you'll be able to see model rank with the best models at the top. And you can compare the variables included in the top models ranked by log posterior odds. So let's see how this works in IBM SPSS Statistics. So I'm in IBM SPSS Statistics, and you can see my data. Now, to get started, I want to go to the Analyze menu and come down to Generalized Linear Models. And here we have Bayesian regression variable selection. Now I'll open it up, and I've moved TV hours into my dependent variable area, and then I've chosen my independent variable. Also, I've chosen my error family and link, and I've asked to display plots. And when I'm ready, I'll click OK and run this. So we have our output. At the top, we have the top models table. So we can view and compare top models, and we can see the variables that are included in those models. And we can also see what the important predictors are: age, education, children, and urban. Now, with the model statistics table, we looked at Model 1, and when we looked at it, it had the highest posterior probability. It also had the highest log marginal likelihood, but it also had an R-square that was similar to Model 2. And Model 1 was the preferred model because it's going to give us the same explanatory power with fewer variables and the higher log marginal likelihood value. We can examine posterior coefficients. These show strong evidence, again, for age, education, children, and urban. We can examine residuals versus fitted. We can also look at the model probabilities plot, model complexity, inclusion probabilities, and finally the heat map. Now, the heat map will show us the rank of the models, so the best models are at the top. We've got log posterior odds and variables. So what we can do is we can look at and evaluate the best models in terms of log posterior odds, and we can see the variables that are included. So now let's talk about permutation tests. So now we have independent samples permutation t-test. Now this does permutation t-test, but it allows for two groups and one variable, or two variables in one group. To install it, you will need to go to the Extensions menu and then click on Extension Hub. Once the Extension Hub is open, you can search for Independent Samples Permutation t-test. You'll just click on Get Extension, and it will download and install it for you. And then to find it, go to the Analyze menu, compare means and proportions, and click on Independent Samples Permutation t-test. There are also permutation tests. Again, you will need to install this, so go to the Extensions menu, select Extension Hub, do a search for permutation tests, click Get Extension. Once it's installed, you can find it when you go to the Analyze menu. You'll click on Regression, and then you can select Permutation Tests. Now, this is a broader extension that supports ANOVA and regression models. It also handles multiple predictors, supports interactions, and will allow for more complex designs. Now, let's look at Independent Samples Permutation t-test. A permutation test is a non-parametric statistical test that's used to determine whether an observed effect is statistically significant. Instead of relying on theoretical distributions, a permutation test builds a sampling distribution directly from the data by reshuffling many times under the assumption that there is no real effect. This is the null hypothesis. They're especially useful when you don't assume normality, sample size is small, data is skewed or irregular, and you want a robust assumption-free test. Now, when you're in the dialog box, you'll take your numeric or scale variable, move it into the first test variable area, and then you'll include your grouping variable. Here, group code is the grouping variable, and I've included the codes here. Now, under two group or two variable permutation test, you also have options. So select your variance assumption, alternative hypothesis, confidence level, number of permutations, and whether or not you'd like a QQ plot. When you run this test, you will receive the t-test settings table and the permutation t-test table. Now, we have two groups. Group 1 has a mean of 10. Group 2 has a mean of 7, so the difference is 3. We can look at the permutation p-value. It is significant. And this indicates that this result is extremely unlikely under the null hypothesis of no difference. Because this result is based on permutations, it remains valid, even though the data are not normally distributed. So let's see how this works in IBM SPSS Statistics. So I want to run my t-test, and you can see here I have the group code column. So 1 is the code for control, 2 is the code for experimental, and I'm comparing these two groups on value. To do this, I want to go to the Analyze menu, select Compare Means and Proportions, and select Independent Samples Permutation t-test. So I'll move value into the first test variable area. So this is my numeric variable. And then group code, I'll move into the grouping variable area. And I'll indicate group 1 and group 2. So these are the codes. For options, I can select my variance assumption, alternative hypothesis, confidence level, and number of permutations. I can also determine whether or not I want to include a QQ plot. Let me click OK and run this. In my output, I have the t-test settings table. So this will show me all the settings that I've chosen. Below this, we have permutation t-tests. We can see the number of cases, t-statistics. You'll be able to see, again, when you come down, the permutation p-value, which tells us that there is a meaningful difference between group 1 and group 2, even after the number of permutations that we have requested. So now we'll cover mixed type cluster with variable selection. Now, this extension you will need to get from the Extensions menu. So to install it, go to the Extensions menu and select Extension Hub. When you're in the Extension Hub, do a search for mixed type cluster with variable selection. You can tick Get Extension, and it will download and install the extension. Now, once it's installed it, to use it, you'll go to the Analyze menu, select Classify, and select Mixed Type Cluster with Variable Selection. Now, this creates a clustering model that uses variable selection, and it will give you the number of clusters. So it's actually quite useful. We'll have a look at building a cluster model using this extension. So what does this procedure do? Well, if you're running cluster analysis, it will automatically select the variables in the number of clusters. It assigns cases to clusters with optional probabilities. It identifies which variables best distinguish groups. It works with continuous, categorical, and count data. The model can be saved and applied to new data. And it handles missing values automatically. A great way to think about it is that it's going to automatically find the best grouping structure in the data while showing you the variables that truly matter, the variables that truly drive the differences between groups. In the dialog box, you'll select your scale and categorical variables. So you can see that I can have a mix of these types of variables. Now for number of clusters, I'll enter the list that I want to test. So 3, 4, 5, 6, and I'm asking it to select variables. I can also determine the variable selection criterion. When I run the cluster analysis in my data, I can see each case in the cluster that it's been assigned to. I can also see for the assignment the probability to that assignment. So these can be included in the data. Here I've just run a frequency procedure on clusters, so I can actually see the size of each cluster. I can also see that I obtained a 6-cluster solution. In our output, it lets us know that variable selection has been performed. It selected 7 variables, so 77.78% of the variables are relevant for clustering. We originally had 9. And it lets me know that predictions have been saved to cluster group 1, 2, 3, 4, 5, and 6. So it's selecting the most useful variables, and it does improve cluster quality because it removes noise. It selects 7 of the 9 variables. It has identified 6 distinct clusters or customer segments. Also, the model can be saved and reused on new data. So here we have output showing discriminative power. And what we see is that income and spend are the dominant drivers of segmentation, while variables like region and satisfaction add almost no value. I can also conduct cluster comparisons. So here, once I have my cluster variable in my data set, I'm looking at the cluster by age, spend, income, number of purchases, and web visits. I can see there are 2 high-value segments, so cluster 2 and 5, which consist of older customers with high average income, frequent purchases, and strong online engagement. I found 2 clusters that consist of younger customers and have limited web engagement. So once you have the cluster membership variable, you can examine it by other variables contained in your data set. What I see is that overall clustering, or the groups, is driven primarily by spend, income, number of purchases, and web engagement. So let's see how this works in IBM SPSS Statistics. Now I want to run my cluster analysis. So to get started, I'll go to Analyze. I'll come down to Classify, and here we have mixed type cluster with variable selection. So I'll click on it. Here you've got scale and categorical variables. So I'm going to move the variables across. So I have multiple variables. I have age, spend, income, gender, region, satisfaction, number of purchases, web visits, newsletter option, and device type. Now I need to indicate the number of clusters. So I'll enter a list. I want it to select variables, and I can choose the variable selection criterion. Now, when I click on options, I need to give a cluster variable name, so I'll just call it cluster. This creates a new variable in the data set called cluster, so each row is assigned into a cluster, and I'll just call the C prob, so this will show me the cluster probability. I also want to show the plot model. So when I'm ready, I'm just going to click OK and run the cluster analysis. In the output, I'll have the clustering parameters table, so I can see the variables that were included, and it says number of clusters to consider. So if you remember, I placed a list. It has the best number of clusters. It has cluster variable, so it created a new variable in the data set called cluster. It has cluster probabilities root. It shows me relevant variables, irrelevant variables, and it shows me the elapsed time. I can also see the discriminative power of each variable. So income and spend are at the top, followed by number of purchases and web visit. At the bottom, we have device type and newsletter option. It also lets me know that variable selection has been performed. 7 of the variables are relevant for clustering. And then it gives me discriminative power. And of course, we can see that income here and spend have the most discriminative power, followed by number of purchases and web visits. Now in our data set, you will have a new variable called cluster. So this customer was assigned to cluster 6, this customer was assigned to cluster 4, this customer was assigned to cluster 2, and you'll be able to see the probability. So The first customer has the highest probability, cluster 6. So the cluster variable is very useful because you can look at cluster and then compare across the clusters age, spend, income, number of purchases, web visits. So the cluster variable will help you compare the various clusters. There are also more new features in IBM SPSS Statistics version 32. So we now have Curated Help Designer. Now here you can add text and color coding to output. You could localize help content into multiple languages. You can share curated help across teams. And this is really ideal when you're working in a training environment, you have audit-sensitive analysis, and you want to reduce misinterpretation. So just as an example, you could use it to make regression output easier to understand. It could highlight which variables are statistically significant, and you can add messages and color coding. So there's now genomic analysis in IBM SPSS Statistics. And this feature bridges genomics research and statistical analysis by allowing researchers to import genomic data and apply statistical procedures without the need for external data conversion tools. So you can import the file types, and this converts genomic data into SPSS data sets for analysis. It can also handle large files. Now, to access the procedure, just go to the Transform menu and select Genomic Analysis, and then you can browse and select for the file types. Finally, we have Output Viewer Enhancement, and here we can selectively unhide columns in output tables. So go to your table, right-click, select Modify Output, and then ask to Show Column. And then the column will reappear in the table. So you can hide the column, and then you can show it again. So that's everything we wanted to show you today. If you want more information on IBM SPSS Statistics, you can visit our website at www.spssanalyticspartner.com. So thanks for watching, and bye for now.